Good afternoon, everyone, and welcome to again another seminar from Gandhinagar and IECS joint initiative. So today Jahanur is here with us. Jahanur did his PhD from IMSC in Chennai on de Sitter and gravitational waves, and then he was a postdoc at CMI and at Charles University in Prague, and currently he is a faculty in Big Spilani, Hyderabad, and also visiting University of Brussels as a Marie Curie Fellow. So Janur, anyway, we'll be talking about DCTEL, which has been his bread and butter, but today about memory effects. So Janur, please.
Okay, thanks, Monto, for the introduction. So I will talk about gravitational memory effect in digital space-time. So this is based on one of my recent work with Geoffrey and Emine. So let's at first, so as my title of my talk is gravitational memory. So let's explain what is gravitational memory. So memory can be think of like a footprint in the space-time. So it can be thought of like a permanent change in the relative separation between test particles, say some freely falling idealized detector or some freely falling observer, and resulting from the passage of the gravitational radiation. So you can think of like if there is a gravitational event at somewhere in the space-time, then you go to the asymptotic regime where the observer or the detector are. Then you can just ask if the gravitational wave passes, then how the relative separation between these test particle changes. And that is the signature of the memory. And how do we quantify memory effect? So as I said, so this is just relative separation between the geodesic. So the best way to measure it, just to compute what is the deviation from the geodesic. So just compute what is your geodesic deviation equation. And the freely falling observer or detector can be modeled as a time-like geodesic in the asymptotic regime of the space-time. And it is therefore expected that memory. Yeah, so can you hear me, or is there a question?
No, it's okay. Please go ahead.
Okay. So as the freely falling inertial observer or detector can be modeled as a time-like geodesic in the asymptotic regime of the space-time, then it is therefore expected that this memory effect can be related to the asymptotic structure of the field also. Okay. Now, this is just a cartoon representation of gravitational memory. If you heard any talk of the memory, you will came across this slide several times. So what? Let's assume a test particle in a circular test particles, and the gravitational waves is going perpendicular to this test particle. Once the gravitational wave passes, then so I have shown here the plus polarization. So it the test particle gets contract and again expand. And if the wave doesn't carry memory, then it if you in the up you can see it goes back in its initial configuration. But if the wave contains memory, then it doesn't go into its initial configuration. So the memory of the space-time stays in these test particles. Okay, so this is just a cartoon representation of a gravitational wave memory. And then you can also ask what happens to the gravitational wave template if the gravitational wave have a memory. I don't see. So, yeah. So can you see a animated video?
Yes.
Yeah. So this basically saying that if the gravitational wave passes perpendicular to this test particle, so then this frequency of the wave get increase, and also the amplitude, and also you can see there's an offset. So if there's a memory, so there should be offset between the field at final time and the initial time. So there's an offset between this line. So this contains the memory effect in the gravitational wave template actually. Okay. So why the understanding of memory is so important? So this is important both conceptually and observationally. As I said previously, gravitational wave template can contain some signature of memory, Actually the
Jahanur,
space, yes.
can you just go back to previous slide?
Yes. This one?
Yeah.
Yeah, maybe I just, yeah.
The end of it, yeah.
Yeah. So end of it, once again, it will just take some time to go. And yes, now.
Yeah, the offset is from the equilibrium, right? That is from the rest position because the wave is up and down. So why is the picture that? I would have expected the whole thing to be
No,
shifted.
so if there is no memory, then there should be no offset, right? So
No. Offset can be the whole ring being shifted. Entire ring will be shifted in some direction, as opposed to being distorted. So distorted is like sending that you cut off the thing at one point.
Okay.
Isn't it? Because the wave amplitude is the offset is changing, so it again reaches its equilibrium position, which is the circle. But the entire circle is shifted either up, down, wherever. Isn't it? I mean,
yeah, that might be. I just
okay, fine.
it somewhere.
Not important, but okay.
Yeah, so I just tried to represent
Okay.
like a cartoon diagram actually.
Okay, fine. Sorry. Carry on.
Okay. So why understanding the memory is important? So this is important both conceptually and observationally. As I said, the gravitational wave template can carry the signature of memory, and I think space-based detector LISA is more prone to detect memory effect. And in my talk, I will focus on the conceptual aspects, and there is renewed attention on memory due to this famous Schrodinger's infrared triangle. So in the three corners of this triangle is memory effect, asymptotic symmetries, and soft theorem. And memory effect and asymptotic symmetries are related by the vacuum transition. And these three apparently different things, like memory effect, as I described previously, asymptotic symmetries, which you can think of like symmetries of the space-time at the far region from some source. So if you have some gravitational event and you go to the far infinity, then you ask what are the symmetries associated with this asymptotic field, then you will get asymptotic symmetries. And all these corners are very well understood in the context of the flat space-time. Now, if you just ask what happens to this infrared triangle in Sitter, so the answer is we don't know several things. And why we should consider de Sitter? I mean, the naive answer is that one of the simplest solution of Einstein vacuum equation in GR, de Sitter is. And the cosmological observation over the years also suggested that our universe is going on accelerated expansion, which is most simplified explained by de Sitter universe. Okay. Now, as I said, de Sitter is very poorly understood. So in this talk, we will discuss about the relation between only memory effect and asymptotic symmetries. And I think the other corners of the infrared triangle is not that much well understood also in de Sitter context. And one of the machinery to connect asymptotic symmetries and memory effect is Bondi-Sachs formalism. So we'll talk about asymptotic symmetries and memory effect in Bondi-Sachs formalism. And also, I must say that asymptotic field are also related to the multiple structure of the source. You can think of it like when you observe, say, gravitational wave event, say, gravitational wave template, you can infer what is the mass or spin of the black hole, right? So looking at the gravitational wave template, actually, you can infer what is the multiple structure of the source. And that's why we want to understand how this asymptotic field actually can be related to the multipolar structure of the source. And this can be achieved in a harmonic gauge or de Donder gauge. And this is my plan of the talk. So at first, I will discuss Bondi-Sachs formalism and asymptotic analysis of a gravitational field and asymptotic symmetries in Bondi-Sachs formalism. And then after that, I will discuss the memory effect. So to compute memory effect, we need to calculate what is the geodesic deviation vector. So we compute geodesic deviation vector and associated memory effect. And then we'll work on harmonic or de Donder gauge. So here we want to relate what is the structure of the asymptotic field is related to the source dynamics via Green's function. I mean, you can think of solving Maxwell's equation with multipolar expansion of the Maxwell equation in presence of some source. Okay. So this harmonic gauge or Detonor gauge has also a lot of application in gravitational generation and data analysis. And so I will discuss all this in the context of de Sitter. Okay. So de Sitter spacetime can be think of like a hyperboloid embedded in a 5-dimensional Minkowski spacetime. And the right hand side is a Penrose diagram of de Sitter spacetime. And if you look at the AB is the future null boundary. So it is space-like, and it is topologically S3. And for our purpose, we will assume there are some spatially compact source near this line AD. So this source can affect only the upper triangle of the space-time, so namely BAD. So for our purpose, it is enough to concentrate on this upper half of the de Sitter, which is called future Poincare patch. Okay, now let's look at how can we set up Bondi-Sachs coordinate in de Sitter space-time. So Bondi-Sachs coordinate are based on outgoing null hypersurface. And if you say that U equals to constant, then you immediately get that GU up component should be 0, and you construct two angular directions so that they are orthogonal to the null direction. Then you will get GUA up to be 0. Then if you write in terms of metric in the down index form, then this GUU up and GUA up goes to GRR down and GRA down equals to 0. So this is a special choice of coordinate system which restrict that metric should be in this form. Okay. So this is the Bondi-Sachs metric in this coordinate, because you see there is no GRR part and no GRA part in this metric. And still we didn't fix what is the radial coordinate. The radial coordinate can be fixed just saying that the determinant of this angular metric can be function of theta phi, function of U and theta phi in general. But Bondi's in his original paper, actually, he took determinant of gamma AB as just determinant of S2. But you can relax that condition more also. So we'll explore linearized Einstein equation, but in a de Sitter background. So here is the de Sitter background metric looks in the Bondi-Sachs coordinate. And this gauge condition GRR and GRA equals to 0 will translate into HRR and HRA equals to 0. And this other determinant condition will goes into the tracelessness of this HAB field. Now we want to plug Bondi's answers in Einstein equation, and this is de Sitter in Bondi-Sachs coordinate.
No, Sudipta
Yeah.
here. So
Yeah.
maybe it's a question ahead of its time, but you may answer it later. But just asking, is this formalism works for strictly de Sitter spacetime, or only asymptotically de Sitter would be enough?
Asymptotically de Sitter will be fine, because there are all the results are available for asymptotically de Sitter spacetime also. I mean, for the purpose of this talk, I'm just taking a de Sitter background and linearized perturbation.
Okay. Another question is that.
Yeah.
Sorry, please complete. Sorry, I cut you.
Yeah. So what I'm saying that this can be done in full nonlinear theory asymptotically de Sitter spacetime.
Another question, you made some point about this gamma AB. So in a pure de Sitter spacetime, gamma AB will be that of S2, right?
Yeah. So in pure de Sitter, gamma AB can be S2, but I mean, I'll come to this later also. I mean, this is related to generalized BMS or BMS.
Okay, yeah.
Hi, Jahanur, can I ask something? So if you have massive sources and in 4 dimensions, are there some, I mean, is this Bondi expansion remains valid, or is there some, like, there are some log terms that get induced? I mean,
so I'm looking at T mu nu equals to 0 equation first.
Yeah. But for the memory, you would, I mean, you will only look at nonlinear memory or also look at linear memory caused by the massive sources?
No, so we still didn't look at the nonlinear memory, but
Only
so
linear memory. So that is massive
only
source.
linear memory, but only also displacement memory. But it is not,
Ah,
I mean,
okay.
it is only displacement memory.
Yeah, but with the linear massive sources in the.
Yes, with the linear massive sources.
And I was just wondering, I mean, I mean, is there a notion of peeling in the setup which is violated by massive sources? Do you know? I mean, maybe it's a tangential,
I mean,
not.
yeah, I mean, peeling is not, I mean, the problem in peeling is that this directional dependence is there, right? I mean,
Yeah,
what do you mean by peeling is not very well defined in Disitter,
I
because
see.
psi 4 doesn't remain invariant if your
So
sky
peeling
class is
itself is
spacely.
subtle. Peeling itself is subtle in the sitter,
Yeah,
even without the
peeling
other side.
itself is subtle. I
I
mean,
see.
I expect that peeling should hold, but what do you mean by psi 4? That is not clear. That is not unique.
Okay. I mean, peeling doesn't hold in 4D with massive sources in flat space. So that's why I was asking. But okay, we can talk about it.
Yeah, we can talk about it. I think there are some work about peeling in Disitter, but not in this in the sense of this invariance of psi 4.
Okay, thanks.
Yeah. Yeah, so now, yeah, so this is the Disitter space-time in Bonisak's coordinate. It basically also covers only the future Poincare patch, and you can think of and the scribe class is here R cross S2 because the two corner points are removed. So you can remove the top left and the point at u equals to plus infinity. So scribe class is here is R cross S2. I mean, you can think of, you can understand it from this background metric also. So if you look at the conformally compactified language, say that you just multiplied with 1 over R square and take R goes to infinity limit, then the background metric is lambda by 3 du square and only sphere metric. So this is the boundary metric of the Disitter in pure Disitter background. Now I want to plug Disitter metric. I want to plug this Bonisak's answers in Einstein equation. So this, all the details of this equation is not important, but important the Einstein equation in Bonisak's answers form a hierarchical partial differential equation. What I mean by that, so if you look at this first equation, this left-hand side is function of beta, but right-hand side is function of only gamma. So given a gamma, I can always solve for beta. Then if you go to the EUA equation, the right-hand side is function of beta and gamma. So I know the beta from the previous equation. Now I plug beta and gamma, then I will extract what is my UA. And then if you look at the V equation, right-hand side is function of beta, UA, and gamma. So from all the previous equation, I know what is my beta, UA, and gamma is my free data, gamma is prescribed. So I can extract what is my V. And also one important thing is that this equation doesn't involve a del U derivative. So that means if you just, okay, so I will explain it later also. So this equation doesn't have the del U derivative. That means if
Jahanur,
you stay,
yes,
yeah,
yeah. So these equations
yeah,
are
go ahead.
just same as Einstein's equation with the source, which is lambda GAB, right?
Yeah, so this equation,
Because
yes.
effectively, I can write Einstein tensor for the boundary metric and add a TAB, which is lambda GAB. It would be
Yeah, but I don't know whether these two things is equivalent because here actually I consider the background is Disitter. So where, and in your case, do you consider that your background is flat or Disitter? So if I just include lambda GAB in terms of source,
Mhm.
then do you consider your background space-time to be flat or Disitter?
But no, I'm saying I'm just writing a generic bondi ansatz without assuming anything about background. Like here also, as far as I can see, lambda only appears in
Yeah, so
one
here
place,
lambda
right?
appears in the Einstein equation, so that R mu nu equals to lambda G mu nu, right?
Yes,
Yeah, so you can think so. Yeah, so this equation is generic actually. So I still didn't consider anything about the background or anything.
exactly. Okay.
Yeah, I think this equation are still generic, so I didn't consider anything. I just plug R min
Okay,
equals to
okay.
lambda G min equation
Sure,
to
sure,
the
sure.
boundary answers.
Thanks.
Okay. So now, yeah, so as I'm saying that this equation doesn't involve any del U derivative. That's why they are called hypersurface equation. So if you just give me some gamma AB on any null slice, then I can extract what is my UA, V, and beta. But those will again will be on the same slice. So it doesn't change the slicing. This equation actually doesn't change the U equals to constant slicing. So this remains on the same hypersurface actually. So that's why they are called hypersurface equation. Now, so given gamma AB, or I just write in terms of linearized field, this is HAB. So HAB is given to us. Then from the Einstein equation, HUA, HUU, and HUR are derived. So I am restricting in the linearized regime. And in the linearized case, actually, you can show that HUR is explicitly zero. I mean, you have to do a gauge transformation. Sometimes this can be think of also a boundary gauge transformation. But if you look at the solution of delta beta, so delta beta also has always a quadratic term. So the linearized delta GUR or HUR is always zero in linearized theory. I think nonlinear theory comes like order R square to the leading order. Okay. Now, so if you look at what is your space time to a nearby slice, say I have all the boundary data in a hypersurface, null hypersurface, then I want to construct what is the nearby hypersurface in the null direction. Then you have to look at this traceless symmetric part of EAB equals to 0 Einstein equation. So that you can see this equation involves del U derivative of HAB. So if I have a HAB in a hypersurface, then this equation actually tells me what is the value of HAB to a nearby hypersurface. That's why I construct the HAB in a nearby hypersurface. Then once I get the value of HAB to a nearby hypersurface, then I will plug again this hypersurface equation to extract all this UR, HUR, HUU, or other thing. And I have to provide some integration constant. So those integration constant are Na and M. So Na is for asymptotically flat spacetime. It is like angular momentum, and this M correspond to the mass in flat spacetime. Okay. Now, there is a non-trivial constraint if you consider there is lambda is non-zero. So namely, if you just look at this transverse tracelet path of this equation, you will get this constraint. And this constraint, I would say, the most non-trivial equation in the de Sitter case. So you can see if lambda is zero, you can put UAB, UB, and QAB to be zero simultaneously. But if you want your cosmological constant is not zero, then you cannot put QAB and UAB, UA to be zero simultaneously. So this is a very non-trivial constraint in the context of de Sitter. So for our case, we'll just use one boundary gauge fixing by saying that UA0 to be zero, and we'll fix the determinant of QAB to be determinant of round sphere metric, but it doesn't necessarily to be QAB is round sphere. So this is like condition for generalized BMS. So now if you look at the answers, you can see this QAB is part of the boundary on SPRI, because it can be understood in terms of conformally compactified space-time. So you just take R equals to 1 over omega, so then multiply with omega square, then take omega goes to 0. Or naively, you can take R to the power minus 2 of all this field, then take R goes to infinity limit. Then you will get only the boundary term is QAB and UA0. So they also, you need this term in de Sitter space-time. So as in this figure actually. So in flat space, you can put both term to be 0, but in de Sitter, you have to fix something QAB or UA on SCRI actually, because they are exactly the boundary data on SCRI. And I think this is consistent with the boundary value problem of de Sitter, because if you put everything to be 0, then your space-time is trivial. Okay, so we'll use this get fixed boundary get fixing condition. Now let's
There is
ask.
a question.
Yeah. Yes,
Yeah.
Jahanur.
Yeah,
There is a question. Sayantan
please.
Ghosh.
Yeah, can I ask a short question like it's
Yes,
probably
yes.
but
Yeah, please go ahead.
sir, so I was asking that in typical 3+1 setting, hello, yeah, in typical 3+1 TV, we take a like space like hypersurface and use the Gauss-Kodaji equation in the foliation on the t direction. So here in the boundary Sachs formulation, you are taking the null surface, right? And you are foliating along the u axis, right? So the one of the null direction. So like what
Yeah.
happens to the v direction? Like can this that is for the accreting sense, or like should we just ignore the v sense because the splitting is now
Yeah,
2
so-
plus 2, right? Yeah, so just
So I am considering only the outgoing waves. So because I'm interested in the outgoing solution, that's why I construct UR theta phi coordinate. And V coordinates will be useful if you want to understand some incoming solution, right?
yeah, but
So
I'm
some
asking that
collapse.
say in the
So
yeah, so in the manifold foliation, like how the say dimension matters, because in 3+1 the foliation is along time axis, the all the Cauchy surfaces are space like. Here the foliation you are missing one of the null, I mean the null direction,
yes,
right?
but
Because it
my
is
foliation is along only u equals to constant surface. The other coordinates is along which grows along u, that is r, and other coordinate is theta phi, right?
oh
So
okay, so
yeah,
your
like
boundary
this.
is okay, okay. So your
So
boundary is just S2, not S3, like I mean, so it's only like a two-dimensional circle.
no, and full
Boundary would be.
I plus is not S2, but what I'm saying that just considering u equals to constant surface and a null hypersurface, the r increases along this null direction, and there are angular coordinates.
Okay, okay, okay. So those are like S2, right? I mean the angular coordinate.
Yeah, angular coordinates are S2,
theta.
yes.
Okay,
Yeah.
okay.
So
No,
it
that's
is
why
not
I got
like
little confused.
double null foliation. It is not that.
Oh, okay. That's what I was wondering, because in 3+1 the dimension is always 4, right? Here it seems like it is only 2+1 because theta phi and u. Oh, okay. So that's what I.
2 plus 1, yeah, it is 4 actually.
Okay.
Theta phi and UR.
Okay. Thank you.
Yeah. So now you can ask what are the asymptotic symmetries of the de Sitter. So asymptotic symmetries by definition are the linearized gravitational field, because linearized gravitational field are always defined up to a gauge transformation of the background. And asymptotic symmetry is generated by these vector fields which preserve this background structure or boundary gauge, and also which preserve the follow-up condition for the linearized field. Okay. And maybe this slide is more technical, but it is just saying that if you just preserve GRR component is 0, just like boundary gauge, so you will fix your xi u to be only function of u and xa. Then you can extract what is your angular field xi b, and then from the tracelessness condition, you will extract what is the r component of the field. And what is non-trivial for de Sitter, once you put this boundary gauge fixing, that UA0 is 0, then you will get a constraint on the derivative of the angular part of the field, YA. And this right-hand side is not 0. So that means YA, this function can depend on U also. I mean, which is not the case for flat space. So flat space, actually, this goes to 0. So in flat space, this YA, angular component of this field, is the only function of theta and phi. But for de Sitter, actually, it depends on U also. And yeah, so other thing I want to mention that if you want to preserve HUR equals to 0 condition, then you will get some constraint on this derivative of F. Okay. So
Sorry,
now,
Janu,
as I said, yeah.
Very silly question. So the first equation I'm a bit confused. So that has no cosmological constant, dou UF minus and F is just
Which one?
super translation generator, right? So why is
Yeah, so F is still super translation generator, but it depends on U and XA.
right? But why is it dependent on YA in this? I mean, I mean, if you take lambda going to 0 limit, then F and YA should just be independent, no? Or maybe I just.
Yeah, so if lambda goes to 0 limit, they are independent, but not
that equation
for
has
lambda
no
non-zero case.
Oh, because the second equation is they're coupled.
Yeah, because of this second equation, actually, they are coupled. So because of this del u ya equation, they are coupled.
But I see. But even if I take lambda to 0, the second equation tells me ya becomes u independent.
Yeah, so if you take lambda goes to 0, then it just reduces like this, right? What you are saying.
But then I go back to the first equation and it still tells me that f is dependent on y. I mean, divergence of y somehow.
No. So the lambda equals to flat space limit is here, right? So once you have del u ya equals to 0, then ya equals
okay. So your f is really f as both. F as super rotation. I mean, f is Lorentz and okay. Thanks.
Yeah, exactly. My f is both.
I was confusing T and F. Thank you.
No. So my f is both T and this part.
Okay.
So once you have this structure, then it will reduce to the flat space thing. But it does for the digital, this is the non-trivial thing. So this doesn't reduce. So because of this derivative depends on the ya derivative depends on lambda.
Thank you.
Okay. Now, so once you have this structure, then this digital group, this lambda BMS group, what I have shown here, it exactly reduced to the generalized BMS because I still didn't fix that my r square r to the power minus 2 of GAB is 0. So if we impose that QAB, the leading order field in the GAB is exactly 0, then you will get BMS. So that your xi ya vector field satisfy the CKV equation. Okay. So then if you look at the vector field which are generated by the super translation T, you can just write it in this form like xi T. And you can think of they generate some angle dependent translation along the u direction actually. And you can think of it like if you just translate u goes to u plus some function of theta and phi, then if you look at your Minkowski metric, that doesn't change. And also that doesn't disrupt any of this follow-up condition because I'm just changing the u direction. So these are the super translation in asymptotically flat space-time. Okay. And now, so let's compute what is the memory effect in flat space-time first. So to compute the memory effect, you just compute what is the geodesic deviation equation. But as we are in the boundary frame, we just want to compute the geodesic deviation equation in the boundary frame. So once you compute the geodesic deviation equation in the boundary frame, and you see to the leading order, it is related to the CR. So if you have SAB is S1 is the geodesic deviation vector. So at the initial time and the final time, if there is gravitational radiation at the initial time and final time, then you can compute what is the geodesic deviation equation, and that geodesic deviation equation is related to the difference in the CAB. And if you remember, in the expansion, CAB is this term, 1 over r term for flat space. Okay. Now you can look at how this supertranslation field actually acts on CAB. So this expression may be a little bit misleading. So what one should do, one should look at what is the Lie derivative of this vector field supertranslation xi on the full GAB. Then you extract what is the R component of that field. Okay. And then you can see that under the supertranslation, only the CAB changes like this form. So what it says, so in Minkowski space-time also, there is some transition of the CAB. If I just put, say, for non-derivative space-time, that means my derivative of the CR is 0. There is no news. But this CAB can be generated by the super translation T. So that is the non-trivial thing. And that's why, I mean, you can use this freedom of T to put CAB at some initial time, but you cannot put CAB to be vanishing in the both initial and final time actually. Because if you look at the memory, so it depends on UI and UF. So you can exploit this delta T freedom in flat space time where your del U CAB is 0 to put CAB either initial or final to be 0. But you cannot put both to be 0 using the same super translation vector field. That's why it says that the memory effect is a transition between this BMS vector field. And now you can ask whether any physical process which can change my CAB. The answer is yes. So if you look at the mass loss formula of Bondi-Sachs formalism, so this I didn't show. But so there are constraints in the HUU term, which is mass, and RUA of this equation actually gives you some evolution equation of this mass. So this basically says if there is a gravitating source, then it emits gravitational waves, which is related to the nu square. Okay. So then if you just integrate this equation, then you will get what is my CAB initial and CAB final. But you need to integrate this last equation actually. So to get what is my delta CAB to relate with the memory effect. Okay. So the upshot is that the leading order memory effect actually depends on the CAB, depends on CR for flat space. Now let's compute what is the geodesic deviation equation in de Sitter. So if you compute that, then you will see immediately this is qualitatively completely different. So I just choose again this Bondi-Sachs formalism, and the leading order geodesic deviation equation depends only on QAB. So QAB, so if you look at, go back to my slide, so QAB is the leading order term of CAB. So in de Sitter, the leading order term in the memory is QAB. So this is actually overleading from the flat space time. So here is the expression for QAB. So this green line are the time like geodesic in de Sitter. So this blue wiggly line is some gravitating source which is emitting gravitational waves between UI to UF. And then you just measure what is the geodesic deviation from UI to UF. Then if you measure that, then you can see that this is proportional to only the QAB metric, only the boundary metric, only the boundary metric on scribe, because previously I explained this QAB is nothing but your initial boundary data on scribe. Okay. Now, again, you can ask the same question, can any physical process generate QAB? The answer is yes. So this is nothing but the delta fluctuation of QAB. So if you look at this equation is more simpler. So this is so in my boundary gauge fixing, if you look at this equation.
It's a small question. So in this case, when you, I mean, there is no past null infinity analog, I guess, right? In the de Sitter case, you just have one null boundary in the de Sitter case. Yeah. So here, how does the shear fall off at large positive and negative U? I mean, because that decay is influenced by the presence of the massive sources in flat space, right?
Yeah.
So here,
that I don't know. I mean, that even in flat space, that u to the power that minus.
Yeah, it's 1 by u if you have massive sources in the far past, right? At spatial infinity, it goes as 1 by u, the shear. So I was wondering
So
here.
you're asking how you actually follow along the u.
At the boundary of the horizon, basically, like how it follows the shear. Or is that not known?
No, in this derivation, actually, I think we didn't use any of this thing, but usually we put some no incoming radiation condition on this upper half, right?
I see. Okay.
So usually you put there is nothing.
It will die down.
So
yeah. But at what rate is it not important? Like to know what the rate of fall off of the shear, or I guess you're saying it's not relevant. I mean, it's not used directly.
Yes, I mean, when we try to relate in terms of, I think the source moment, then I think we use the retarded Green's function. That's why you put the no incoming condition from the past. Past mean, I mean this lower triangle, lower half of this diagram.
Okay, thanks.
And yeah, so is there a question?
Yeah, Jahanur, I have one question. I'm Amitabh here.
Yeah.
Yeah, so this equation that you have written, this is in the gauge where UA0 is 0.
UA0 is 0. I mean, you mean VA0.
No, the boundary condition.
UA0 equals to, UA0 equals to 0. Yes.
Okay. So, so when you say that the equation crucially depends on QAB, is in your gauge choice. I mean, if you turn on UA0 to be non-zero, then of course that equation will have some those terms.
Yes. Yes. And also, so what I want to mention further is that, so then you can ask whether this QAB can be changed by some sources, then you will get a simple equation from this constraint equation actually. So if you look at UA equals to 0, this constraint equation only reduced to del U QAB equals to lambda by 3 CAB related to the shear. I mean, this is completely a new flux law for de Sitter. So there is no analog of this balance law in flat space time. So then if you want to compute what is my QAB initial and QAB final, you just integrate this equation, right? So then you compute what is the UI and UF final.
Well, John,
Integrate
just to
that equation.
ask again, I mean, so here it's clear that if your C fell off as 1 by U at late U, like in flat space, then your Q will have logarithmic divergence at late U, right? I mean,
yeah, so if CAB has the follow-up of, you are
as 1
saying
by U,
one
which is
U,
what happens in the flat case, right? And so is there a good reason to believe that the integral is convergent, basically, if you take UF to infinity or UI to infinity?
Yeah, that, I mean,
or what if your Q has a logarithmic divergence in U? Is it still like asymptotically de Sitter or something is, I mean, would you still call it asymptotically de Sitter?
Yeah, that I don't know, because we didn't consider any follow-up of U follow-up of
Yes,
CAB
okay.
actually, because we just construct like the solution. So CAB is function of only U theta phi. Yeah,
Okay,
that
okay.
will be interesting question actually.
I will ask you later. Yeah. Bye.
Okay.
So,
Okay.
Jahanur, one question. Sudipto here.
Yeah.
Just one question. So, this new flux law, what does it mean? Does it mean there are new charges in the theory?
No, I mean, this basically, I mean, I'm calling it flux law because of this constraint equation actually. So it is not related to like anything charge or kind of thing. I'm just calling it just balance law from this constraint equation.
Okay. Right. Because in black hole thermodynamics in de Sitter, lambda enters as a charge.
I see.
This has nothing to do with those kind of things, right? Well, so, for example, if I want something like a smart formula for including gravitational radiation, will this flux law imprint new charges on it or proportional to lambda or something?
Yeah, I mean, for now, I cannot comment on that. Yes, smart formula, you can just look at this entropy, right? And whether, I mean, whether this del QAB is related to some charge or related to thing that, that I don't know.
Okay, thank you.
Yeah, so I'm calling it the balance law because of this constraint equation actually.
Okay, thank you.
Jahanur, can I ask one more question?
Yeah, sure.
So, as you are saying that there is a difference between flat space and de Sitter case regarding this balance law and others. So, in flat space, usually one turn on some energy momentum tensor, right? Shockwave kind of thing, and then relates the initial and final vacuum.
So, so basically this equation, right? The equation at the bottom.
Yeah. But here you have not turned on anything else.
No, because here everything is overleading. So I don't need to turn on anything to the leading order effect. Because if you look at this is overleading effect. So this is because this depends on delta QAB, right?
Yeah, I mean,
so that's why I don't need that conservation equation. I mean, I don't need mass loss formula to relate my boundary fluctuation. That is my point. Right. So here, if you look at this delta CAB, you always need a mass loss formula to relate that, right? Where is that? So if you look at this, so if you want to compute what is my difference in shear, you have to always use this mass loss formula, right?
Last equation, yeah.
Yes, so in de Sitter, we have also some analog of mass loss formula, but to compute what is the difference between QAB, I don't need that because it is more subleading in de Sitter.
I see. Okay.
It is kind of overleading effect compared to the flat space. So that's why I cannot see in flat space, right?
So the memory effect that we understand from the flat space perspective, that understanding also changes, and the way we understand memory effect.
Yes,
right. So it's no longer the same, right?
Yeah, it is qualitatively different in the sense that this term is overleading compared to the flat space. And if you match with the flat space term, then you need to compute one more lower order term in de Sitter, right? Because it has nothing to do with any transition of delta CAB. I mean, it doesn't
Right.
come like delta CAB, right? Because if you look at, I mean, it comes from the geodesic equation also, that is also consistent. Because
Yeah,
it
yeah.
just
That I've
cares
seen.
about your boundary metric QAB, but in flat space, I can put QAB to be 0, right? So in the flat space, that the leading term is CAB, right?
Hmm.
So here the leading term, you cannot turn off the leading term. So I mean, if you turn off the leading term, then there is no dynamics in your space time.
Right, right, right.
So that's why, I mean, it is
Yes.
overleading compared to flat space.
I mean, I mean, at this moment, it's not clear that the other corner of the triangle, uh, soft theory, which is far from being
Yeah,
reached,
I
but
mean,
there is no way to address that issue probably.
yeah, that I don't know. I mean, that I don't know completely.
Yeah, I mean, since this is as you are saying that this is QAB is there and the
Yeah.
leading order, so it's
So
difficult. I mean,
yeah, so
difficult
I
to give
mean,
analogous
yeah, I
definitions
mean,
of
in de Sitter, I mean, if you want CAB to be in your theory, you cannot turn off your boundary fluctuation completely. That
completely.
is the
Yeah.
point. I mean, I think that is consistent with the initial value problem in de Sitter also. I mean, you cannot put your boundary data completely 0. I mean, if you put boundary data completely 0, then the space-time is trivial.
Hmm.
Okay.
Okay.
Yeah. So now, as I said, so this is completely a different feature from flat space. And hi, can you hear me?
Yes, we can. Yeah.
Okay. Yeah, so this is completely a different feature from flat space. And then you can ask, what is the boundary metric fluctuation can be generated from some spatially compact source? And can one relate some lambda BMS kind of transition from these gravitational waves? And I will just want to ask how much time I have.
Well, you can take another 15 minutes. Yeah.
Okay, so then I'll just briefly go through it. Okay, so then you ask how your boundary metric QAB can be related to the some source dynamics of the de Sitter, just like some spatially compact source. So you do the same analysis what you do in textbook GR. You understand the linearized field and then write in terms of this wave equation and try to solve the wave equation in terms of Green's function. So once you solve the Green's function equation, then you use the conservation equation to relate d3x Tij with Qij, because here I want to understand how my QAB can be generated from some source integral, from some multipolar structure of the source, just like flat space, you can ask. Okay, so then you just follow the same prescription, but in the de Sitter background. Okay, so I mean, here we exclusively work on conformally flat patch of the de Sitter, which again covers this upper half of the triangle. And then this in eta or theta phi, it is conformally flat. And this reduces a lot of computational cost. And then you just define a trace reverse component. Then you choose a gauge, which I did in my PhD with that also. So then you just decompose, use this gauge, and the advantage of using this gauge, actually, all the equation becomes decoupled, because as the background is curved, so a priori it is not clear whether all this equation of the perturbation is decoupled or not. So using this gauge actually makes all the equation decoupled in terms of this variable chi hat, which is chi 0, 0, which is not exactly trace of the 4D, but it is chi 0, 0 down, chi ij contracted with delta, and chi 0 I, chi ij. And then you want to ask, how can I solve this in terms of Green's function? Yes, you can solve this. So if you look at this chi ij equation, you can solve this in terms of Green's function, and you can see Green's function has a delta and theta parts. So delta part means that the propagation is along the light cone, and there is a theta part which says that the propagation can be inside the light cone, which is some generic feature of any curved background, such that if the wave propagates, it backscatter, and then it can be inside the light cone also. So that actually generates this theta term. Actually, in the if you just solve in terms of chi ij, generate a tail integral. It's going from -infinity to eta retarded. So basically, this tail integral says the field at point eta and x doesn't depend only the retarded history of the source, but it depends on all the past memory of the source also. Okay. Now, so we want to relate this d3x tij, what we did in the flat space time, d3x tij in terms of qij. So similarly, the same thing we want to do for the de Sitter case. So for that, we need to define moment. So the definition of moment in de Sitter is also tricky. So you need to define a moment like a coordinate scalar. So you construct some tetrad in de Sitter frame, and you then define the moment with respect to that tetrad frame, because this tetrad frame will be just only scale factor times e, because there is overall scale factor. So you can easily construct the tetrad. So once given the tetrad, you can just compute what this tetrad component, and then you just go to the tensor component actually. So here all this L, I mean, this is multi-index tensor. So if I just say Qij rho, so this is T00 xi xj. So these are multi-index. So XL means there is X up to L. So if I mean Xij, that means Xi xj. And similarly here, so say if I say Qij rho, so this integral is T00 xi xj. Similarly, I can put any index. So if I say Qij k, so this integral is T00 xi xj k. Okay. So then you use the conservation equation to relate different moment. So these are Qij rho are the mass moment, Pi, these are the momentum moment. So this is related to T0i, just like flat space, but you will get all the scale factor actually. And Sij is the stress moment. So you just compute Tij contracted with S. And this last two equation is the conservation equation. Then the trick is that you need to, if you want to really extract what is your quadrupolar order, you need a quadrupolar truncation. So by quadrupolar truncation, I mean if there is an index L greater than 2, that means T mu nu xi xj greater than 2, that should be 0. Okay, so this is the quadrupolar truncation. And also, if you look at the conservation equation, that satisfies some other constraint, namely this kind of constraint. And also, we want to represent all L equals to 0, L equals to 1, and L equals to 2 mode, just like SO3 decomposition. So we want to construct what are the dipoles, what are the odd parity quadrupoles, and what are the even parity quadrupoles. So even parity quadrupoles are Qij. So what is important to realize, you can look at this Sij piece. So this is basically d3x Tij xk xl, but they involves in Qij term. Okay. So, but this integral, so this Sij kl by definition, so I just put the 2 index kl, so this becomes Tij xk xl. Okay. But this contains Qij term. Okay. So if you look at this one, and then we defined other moments. So those those details are not that important. So then we try to solve this linearized equation, and we assume that there are source near the line AD, and you assume that source is well enough inside the cosmological horizon, namely this d by rho is much less than 1. So d is the coordinate dimension of the source. Then we assume that the physical size of the source at any retarded instant is well inside the cosmological horizon actually. So then you will get this constraint. And this is also related to the fact that if you look at if you want to reach scry, you need to go to eta equals to 0. So in de Sitter, actually rho goes to infinity, doesn't get you on sky, but you have to really go to the late time. So the expansion parameter in de Sitter should be always eta over rho, not 1 over rho compared to the flat space case. Okay. So also, because you have to integrate this chi-ij expression, so we also assume for the validity of the Taylor series that this source is also slowly varying. Okay. And then if you just plug all this expression, so you will get this expression which has one. So I just decompose it like so the structure of this equation is important because the first term is the leading term. So there is no 1 over rho term here. So this is like QAB term, what I have shown in the Bondi-Sachs case. So this is my boundary metric kind of thing. And every expansion parameter comes with the factor 1 over eta rho. So this is 1 over a eta is minus h eta. So the expansion parameter is exactly eta over rho. Similarly, this one. So this is up to the quadrupolar order. So I must say there is some issue in the quadrupolar truncation in the previous work, which is done by ABK, Abhay Astekar, and some of my PhD work. So what we did, we just focus on the leading order term. So what we did, we just look at the leading order term. The catch is that this Sijkl, so if you look at the Sijkl, so they can generate QP term actually from the higher order term in the Taylor series expansion. And those QP term actually exactly cancels with the QP term in this 1 over R piece. So if you look at this 1 over eta rho, there is no QP term in the which depends on H. So that is because they exactly cancels out with the higher order term from Sijkl. Okay.
Sorry, Jahanur,
so this can, yeah.
So I thought you want to compute for CAB, right? In the end, you want to compute CAB.
QAB, CAB, everything I can compute.
Yeah, I know, but as you said, like once I know CAB, I can compute at least a change in Q using the flux.
Yeah.
So, but this chi is defined by some rescaling with 1 by a square, etc.
Yeah, that we can incorporate. I mean, I just do a coordinate transformation from Bondi gauge from the harmonic gauge to Bondi gauge, and I can plug in all the scale factor, and we took care of that, all these things.
So how is C behaving with you then? I mean, in your coordinates?
QAB, I don't have. Yeah, so I'll show the expression for QAB. I think
Okay.
So let me just go ahead. I will see. So this can be also understood as the mode decomposition in spherical harmonics. Actually, if you just write down chi-ij, then I can ask what is the, I can write it in terms of spherical harmonics, whether it can exactly generate the L equals to 2 mode for the quadrupolar level. So the answer is yes. So, and the answer also confirmed that there are some issue in the previous works. So this work is ongoing with Amitabh and Hers and Shitender. Also now, how can I relate? So these are my solution in the generalized harmonic gauge. How can I relate with this all this Bondi-Sachs variable? So that the usual prescription is that just do a coordinate transformation. But not only the coordinate transformation works, but you have to also put the perturbation in the Bondi gauge, right? And also I did also the boundary gauge fixing I am working on. So if I just take care of all these things, then I can relate my boundary metric QAB in terms of all these moments. So this is the expression for QAB in terms of moment. Yeah, so if you look at this one, and by the boundary gauge fixing, actually this zeta ij satisfies some equation. And if I just assume that my Qij rho plus P has some step function with theta, then I can compute what is my xi ij and derivative of xi ij. And you can see there is a xi b0 involved, which is related to the asymptotic symmetries actually. Then I can use the lambda BMS generator vector, which has exactly this structure.
Notation. So you have U, UF, and UI. I mean, what are the? You have U and UF, and I mean you're computing the delta QB at U, right? At some U.
Yeah. So no, so this notation is a little bit yeah. So this is basically So at particular U. So this is not
QIJ, the QIJ rho plus P as a function of U. What is UI and UF there now? Is it infinity and minus infinity, or in the equation for QIJ?
Yeah. So in the equation
you have some UI and UF. I mean, what are those?
So this one. Yeah, because I'm just considering a step function actually. So I am just saying that my Qij rho u is just a step function.
So ui is minus infinity or plus infinity, and uf is the other. Is that okay? Is that okay to?
I just consider some transient wave, so I just put
Okay, fine.
ui.
Thanks.
Yeah, so it is not exactly minus infinity, but some transient wave. Actually.
Okay.
Yeah, so I just model that so that I can solve this equation actually, because solving this zeta ij equation is very tricky. I don't know. So that's why we just choose a simple answers. Say that if my Qij rho plus p had some theta function, step function, then how can I compute what is my zeta ij? Because this zeta ij I want to compute for the QAB, right? So once you compute that, then you will see the structure is exactly same to the lambda BMS generator. So the lambda BMS generator are previously I have shown, maybe I will go back a little bit later. So these are the same structure as the lambda BMS generator. So then you can use this lambda BMS generator to put one of the QAB at initial or final to be 0, just like flat space. You cannot set CAB on the both UI and UF, but you can at least put at initial time or final time. The same thing goes over here. So this is like a lambda BMS transition. So the signature of non-zeroness of QAB is the signature of lambda BMS transition. So that's why this diagram. So I turn on my source between UI to UF. So this is lambda BMS vacuum before that, and then after that also there is in between there is some radiation. Okay. So
but
then yeah.
Your equation for your previous equation has a. I mean, if you go to the equation before this, so you see your zeta ij. I mean, there's a cosh hyperbolic, with a step function, right? So at large u, I mean, you have some like exponential growth in the sphere metric now, because delta q is proportional to dou u of zeta, as far as I understand from the top equation. You know, zeta ij grows like at u going to plus infinity, it's growing like as exponential, right? So, I mean, physically, how do I understand this? Like, I mean, I have like is it far away from the source? My sphere metric is like fluctuating like uncontrollably somehow. Is it? I mean, what is the, and you have a source which was slowly varying also. So what is this large? I mean, what is, I mean, physically, how do I understand this uncontrollable fluctuation in Q at plus infinity as u goes to plus infinity?
Yeah, plus infinity.
I mean, the zeta, as far as I understand, zeta is diverging, exponentially diverging at plus infinity, and then it looks like delta q is also diverging. And is that, I don't know, is that physically seems very counterintuitive, right?
Yeah, I mean, this is counter, but yeah, this is counterintuitive.
Because there's a
but I mean, derivative of
derivative, but okay, I mean, it's just one derivative.
Yeah, one derivative, but this one derivative goes as sine hyperbolic, right?
Well, I mean, I'm saying at plus infinity will still exponentially diverge. I mean, there's a theta function there, so there'll be one term which is just
and derivative will also give you exponential.
Yeah, I mean,
yeah, derivative will give you also an exponential. I mean, this we just construct to just get a solution of this equation actually, I think, and also that fits with the I understand.
You have a slowly varying compactly supported source, and now you are saying that it creates enough radiation that it can make the sphere metric fluctuations wild. I mean, this seems okay. I guess in this iter, because of inflating space, many things, crazy things can happen. Maybe that's the signature of this iter, right? I mean, maybe because h is, of course, h is present in the exponent. So
yeah.
But anyway, yeah, thanks.
Yeah, so this I will think, because yeah, so we just construct this solution because we want to just look at what we can construct a solution for zeta ij or not, and whether it can be mapped to the lambda BMS thing. Yeah, so as I said, so you can just put one UI or UF like QAB to be the round metric, but not in the both place. Yeah, so as I said, here's the summary slide. So maybe I can just leave it here, or yeah, maybe it's good to take questions.
So this deviation of the metric can be generalized for the non-local theory of gravity.
So generalization of the which metric?
The deviation, the geodesic deviation, the memory effect,
Yeah.
So can we think about this like a non-local effects in the gravity? So just like a non-local electrodynamics, there are some memory effects due to the non-local electrodynamics.
I don't. So is there any, you can compute any analog of geodesic deviation equation? I'm not.
I mean that we are studying here the memory effects in the gravitational wave. So my question is, there are some few memory effects in the non-local electrodynamics. So similarly, can we construct some non-local gravity theory?
Yeah, that I don't know. I mean, if you can write down geodesic deviation equation, I guess yes, but I'm not sure. I don't know.
Okay, sir. Thank you.
Shantan has a question.
Yeah, it is a little generic question. So, like, your de Sitter metric was already known. Like, I mean, it would just get a lambda r squared one. So, I am saying that, let's say, instead of de Sitter, let's say I take lambda r cube or like lambda r. I mean, the source doesn't matter. Let's say, just for sake of mathematics, if I take a background like lambda r cube or lambda r, so how does the C effect changes? Like, I mean, is it very susceptible to say lambda r square itself? I mean, I understand the infinity, etc. for de Sitter is very well known, the chi plus, etc. So I'm just asking that if I just change the metric to, just for curiosity, lambda r cube or r to the power 4, how does the analysis changes? Like, I mean, is it very susceptible to that? Yeah, like the Green's function, all the C or the memory heuristic?
Yeah, I mean, obviously it is very much sensitive to the background structure. But if I change it, some, I mean, you want to change this background metric itself, lambda r square 3 itself.
Yeah, so if I take say lambda r, let's say little bit subdominant. I mean, forget about T mu nu. You can get T mu nu by back tracing. So would the CA be like the memory effect still persists, or there are asymptotic changes like the 1 by r or r squared, etc. that would mess it up? So I'm asking that how susceptible is to the r squared? I mean, the de Sitter is always r squared, but say I change the power to for mathematical curiosity. So like, I mean, how the asymptotic and C, all those memory effect would last, or is it be subdominant, super dominant? I mean, it is still non-asymptotic.
Yes, I mean, a priori this should affect somehow in the background curvature, and I mean, you need to compute what is your all this connection, right? I mean, a priori I don't have any comment, but I think it should affect.
Okay. No, that's why I'm asking that could this be generalized to some FR like which is non-asymptotically flat? So like could the generalize all these things would work out? Like if I take 1 minus say f of r where r is some polynomial. Like, I mean, just asking that. Oh, would the r power n would like somewhat give us? Okay.
Yeah, I think it can be generalized, but a priori I cannot just comment on what is the other follow-up condition, right? And it should be sensitive of this function also, because it all this computation of this background connection goes into that.
Because if I take root r, I mean, that is not also asymptotically flat, right? But it seems like root r would be a little bit subdominant in the when you calculated the CAB, etc. Like if I take lambda root r or something. So there could be like asymptotic non-flat space-time, which doesn't have that much memory effect or that dies out, etc. That's what I'm asking.
Yeah, that can be. I mean, in principle, you can consider some other class of space-time also. But whether what is the leading order effect should be, I mean, that I cannot comment on. Right.
And just asking that for ADS spaces, could it be generalized? I mean, I understand that global structure is very defined, but say I want to do a local, say, Poincare patch over if I do the metric over Poincare patch, like would there be still one side effect also?
Yeah, I think. But I think for ADS case also people have studied, but ADS is more people studied like reflecting boundary condition. I mean, to me, ADS, I mean, the meaning of propagation in ADS, I don't know. What is the outgoing condition in the ADS? What is the outgoing radiation condition? I mean, people have studied. You can just like leaky boundary condition in ADS, Geoffrey, and all these people. I mean, whatever we have derived for lambda greater than 0. I mean, they said that yes, that can be generalized for lambda less than 0 also. In that sense, if you just consider just like it is something leaking to the boundary, then yes. But if you consider some reflecting boundary condition, then everything, I mean, then all this, I mean, then all the CAB and all these things, that should be 0, right?
No, I asked because the topology is entirely different, right? One is Sn cross R and another one is R cross S1. So that's what I was wondering that. So the global structure.
I think for ADS, it can be generalized, but we have done with the leaky boundary condition, yes.
Thank you very much, sir. Nice.
Okay, I think Ghanshyam, you have a question, right? Hello.
Yeah. Yes, I have some very elementary questions. A couple of them. One, you assume that the source was static in the past and in the future.
Yes. Both.
But but in de Sitter, we know it's not possible, right? You ignore it, but the mass moment is not conserved. So
no,
it
mass
always has
moment. I mean,
tau derivative, only derivative of the your Q integral T00.
The integral T00, I think there is some conservation law which is analog to mass moment. I mean, what we define in the mass moment in our paper, that is not one. So here the mass moment is different.
No, that's okay. Okay, so whatever referring to our notation, whatever that is not conserved, because analog of mass being conserved in the flat space, there is no corresponding statement in the de Sitter. So the source is never static. That was one of the things.
Yes, but the thing is that if you just put that derivative of Qij rho, then your Chi should be 0, right?
Okay, let me ask you more questions, which are like I don't know. I mean, I can't see it translate so fast. But this is one question, because you have made this point in our paper that in de Sitter, the stress tensor cannot be completely static, even if using d derivative terms and so on.
No, say it again.
The source term, it can never be exactly static in de Sitter because of the curvature effect. Curvature is always there. So source is never completely static. That's the point we have made in our paper also. I mean, we use the equation what we call M that time, which delta of M is equal to proportional to lambda, square root of lambda by 3 h time. You also have the same equation in your paper. It's not, I checked that. In your paper also you have the equation. But let me go to the next question, which is, this is just one point. Other is, this pi plus in de Sitter is never accessible to the observer. So where are you going to put your the memory?
That is not
so
exactly.
you may calculate it mathematically. That's fine. But can you translate it to the cosmological horizon? So that's where you can make the measurement.
I don't think that statement is also true entirely.
Go to your slide 25.
Yeah, so this one. So so I can also, because these are always a time-like separated, right? So the space-like separation between after cosmological horizon, if I just consider the 2 point after the cosmological horizon, but if I start from here in this right corner, this is always time-like.
No, that's fine.
So, I mean, that's why actually you can say in ET, you can see the gravitational wave from the cosmological horizon is
your diagram is fine. I have nothing against it. That's fine. The time like curves are perfectly fine. But you will put your detector 2 arms or 2 geodesics which are going to be showing the memory effect. If they show the effect, that should be visible to me, which is in the left corner. But if I cross the cosmological, I can never see what is there, what is happening there. It will happen, but I won't know.
Yeah, you can compute. So one can compute on the.
You can compute, but so my question is, can you translate this relay into the either near the cosmological horizon? In which case, that's okay. It's a computational tool which is convenient. That's fine.
I think truncation to the cosmological horizon can be done, but the thing, so that actually I didn't look at. I mean, you need to just model your detector in some sense that, I think
that geodesic, but it has to be seen
truncation to the cosmological horizon.
You have to translate the results from the sky plus to that. Then you can detect. Otherwise, how can you detect?
Yeah, I mean, our prescription is not just to, not to, what we saw that, okay, so you just compute everything on sky, what people do, but we did also. So that is, we are not saying that this is the, we are not modeling the detector. So that is
no. I mean, I'm not getting my point. That is correct. I'm nothing against the computation. You can still compute it in there, but you should be able to translate that computation to detect memory effect or define and identify memory effect inside the horizon.
Yes, that is true. That is true.
Once you do that, that's okay. That's
yeah. So you just cut off everything on the cosmological horizon and then compute everything on the cosmological horizon itself.
And as to see whether there is an ambiguity involved in that, in defining it. I don't know. I'm just raising the question.
Okay. So you expect there to be ambiguity on cosmological horizon?
No, typically you see you take the limit minus infinity and plus infinity, difference between that as this, right? Yeah. So you have to define which is memory you're computing.
Okay.
I don't know. I'm just thinking about it. Anyway, the main point is whether you can translate the results from the sky plus to inside the cosmological horizon.
Amitabh wants to add to something.
Yeah, actually, just to answer your first question, I think what you are saying is that Q rho is not conserved. I mean, del U of Q rho is not 0. But one can write down the conservation equation such that, I mean, one can write down the conservation solution in a monopole solution such that it satisfies some sort of
so just like you construct L equals to 0 mode. So this L equals to 0 mode, it doesn't involve only Q rho for de Sitter.
Okay.
Right. So you can just, and L equals to 1 mode. Yeah, I think L equals to 1 mode is not conserved, but L equals to 0 mode is conserved.
Oh, okay. Okay, then it's a different point.
Because I mean that's why I said that mass term doesn't come with only Q rho. That's why I said actually.
Okay, fine.
It comes with some combination actually.
Well, if there is some, okay, fine, that's fair enough. So you can have your statement is no matter how you characterize it, your source can be static.
Yeah, like
yes,
that's a physical statement, not related to how you define it and so on.
Yeah. I mean, linearization or short shell black hole in de Sitter would be static source. And the question is how the mass is identified with these source moments. So that exercise one can do.
No. I don't want everything to be permanently static. It has to be static in the past and future. In between, it has to radiate.
That I don't know.
Okay.
I think we discuss it more. Yeah. Please
it's not going to be resolved here. Yeah.
Yeah. Sure.
Okay. Any other question? Please go ahead and ask if you have any other question. Okay, if it is not, let us thank Jahanur for this very wonderful talk, and we also have a very illuminating discussion. And thanks a lot, Jahanur, and please stay tuned for the next talks of the part of this series. Thank you. Thanks a lot.
Okay, thanks.
See you guys.
Okay, thank you.
Okay.
See you. Bye.